Okay, I want to start on chapter 34 today on ray optics. And with ray optics, we talked about waves last time, and we basically finished up and said when waves are about 1,000 times to the size of what we're looking at, then we got to use the wave phenomenon. Once for light, once you start dealing with things less than about a millimeter or so, about half a millimeter, maybe less than half a millimeter, gaps, openings, things like that, diffraction effects occurs, wave phenomenon. But most of the things we deal with light being such a small wavelength, electromagnetic radiation, we can ignore those effects many times. And the idea, Newton came up with this idea of ray optics. It's a model that works in many situations. Again, remembering that when the wavelength is much smaller than the openings, the size of the openings, and things we're dealing with, that ray nature works. If you get less than that, when we talk about the wave model, when you're getting close to 1,000 times bigger than that size of the wave that you're looking at, the wavelength of it, then you really need to start about diffraction effects are going to come into play if you're not careful. All right. So we're going to look at some wave effects. This ray model of light. This is chapter 34. And what you were taught in physical science, what you may have been taught in another class, in a physics class, a lot of what you were taught was probably this ray model of light. Its works, and that's 34.1, I should say, is ray model of light. Chapter 34 is ray optics. My bad there. My bad. Okay. So let's define terms. What's a light ray? A light ray is just a line in the direction the light energy is flowing. It's just a line in that direction. That's all it is. It's a representation, of course. It's a model. Now, what do we know about that model? In this model, light rays travel in straight lines. Woohoo! That makes them easy. It's like a laser goes out. Travels in straight lines. They travel forever unless they interact with something. Most of the time, that's something that matters. And that's a bad joke, of course, if you read the book. But it interacts with something. It's going to keep going straight unless something interacts with it. What we call the object is the source of the rays. Now, for me, if you form an image of me with a mirror or a lens, you would say I'm the object, so I'm the source of the light rays. I may have a glowing personality. I may be very bright as a person. I may be the light of your life, this class may be. But I am not the source of the light rays. I do not emanate, maybe infrared. But visible light, I am not glowing and everything in light. Now, I am the source of the rays compared to the image and in this model, but light is from the lights in the room and everything are reflecting off me, and then that's going through the system, through the optical system. And then that forms an image. I am not, when I say source, doesn't mean you're emanating it. Most of the time, I mean, it can be, but for a lot of images that you'll do, unless it's like a light bulb imaging, something like that, it doesn't actually glow and give off the light. So make sure might be splitting hairs there, but I want to make sure you understand the difference. Eyes, when we look at things with our eyes see by focusing divergent bundles of light rays. I'll say extend backwards. Our eyes see rays coming to us, and we assume, our brain, the way it processes, assuming that light coming to us kept going straight. So it went straight out. It makes that assumption. Okay. Makes that assumption. So like in a microscope, you know, if you've seen like ray diagrams for microscopes, we'll get into that. You'll see the eye basically, for a microscope that we would use an eye for, it's extending those light rays, and that's how it forms that big magnified image that you see. That's the basic model. That's the basic model. Okay? Now, for these objects, a couple things. Light rays are there if you see them or not. If a tree falls in the woods, does it make a sound? Well, light rays are there whether you see them or not. They're actually physically there. They're that energy of that light traveling forward. Most of the time, what we deal with, we always say most of the time, lots of the times what we're going to deal with are parallel light rays. So in that case, you got light all coming in this direction. Now sometimes you can have a point source of light. It's like a light bulb. I guess I had that idea. If you had a light bulb, and they all come out like this. Of course, we know the light like this always makes white t-shirts glow because that's a black light. Okay, that's enough of the jokes. All right. What do we use with these? We're going to make ray diagrams. To form images. And that's how we can predict where these images will be. And in our optical system, you want to be able to predict what you see from that. What's interesting, and really a good application, is there's something called, the book talks about apertures. And an aperture is, there's lots of ways. An aperture is just closing up a complete opening. If I want to make an aperture, think of an aperture as it's an opening light can go through. For a lot of optical systems, the lenses themselves, the edge of those lenses, they form the aperture because light can't go through past the edge of the lens. But if I put, this is a polarizer from the other day, and I'm going to put this in front and say it only, and I put a thing around the edge here so you don't see light coming in from the sides. You would only see light that went through this circular opening. And on camera, sometimes you'll see a little opening go, you know, all that stuff. And when it does that, what you're changing the aperture. Now with cameras, there's a term called aperture stop. That's basically how much light it lets in. Think of a digital camera. Think if you have a digital camera, if it saturates, so it's so bright you can't see any detail, or something, so you're angled at the sun or whatever, one of the ways to reduce that brightness is aperture down the system. In other words, have a little opening there that kind of closes down, so you're only looking through a little bitty hole. And that looking through that little bitty hole blocks off a lot of that light. Now, that's a function of apertures, one of the functions of apertures in modern day camera systems, that they set how much light gets through a system. There's something called a camera obscura. And I used to really enjoy these things. I've read up a lot about these. Camera obscuras are also known as pinhole cameras. Some of the spy cameras today actually we're using a pinhole camera. That means the real cheapies without a little lens. Lenses are so cheap now, you might as well put one. You don't need to do this. Plastic lenses and stuff like that, the fabrication techniques are so cheap. But with these pinhole type cameras, basically it uses, if you want to think of a pinhole camera, has a little opening there. And let's draw something out here. Let's draw an elephant. Tail. Okay. That's our elephant, right? Oops, gotta draw some eyes. He's a happy elephant. Alright? That's an elephant. Okay? Alright. You don't think it's an elephant, Cameron? I really don't care what you think, Cameron. Understand? If that's an elephant or not. I really don't care if you don't think it's an elephant. MLA, is that an elephant? Of course it's an elephant. Got it right there. Alright. So let's look at this. So this elephant, and I'm going to draw this, let me draw this in black. And what a camera obscura does, it takes, and this little pinhole acts as kind of like a lens, but effectively, you take a light ray from here, and it'll go down to the bottom. A light ray from here will go up the top. And here it will go down actually further. I probably need to extend that down. Run out of board space. But this camera obscura will actually form an image, a soft image. It's not a little bright one. Not all the light from this that emits from this point or comes from this point goes straight in. It's coming off at angles. But you'll get a faint image formed on this back screen. Excuse me. Now, this image can be a little fuzzy because what happens is this point here, say at the top of that elephant's shoulders and stuff, it could go through that top and it also could go through that bottom. So you take a point and it goes through this pinhole and it kind of gets over, that point gets spread out over a little area, so that makes it a little blurry. So when you spread out those points on this, it makes it blurry. So you get a little bit of a blurry image, not a lot, especially with a small pinhole. If it's really bright outside, you can get a brighter image inside. But the Romans actually understood this, and that was, like you go to a Roman party, and I assume if you're Romans, you do other things than camera obscuras, but at parties. But part of what you did sometimes, or an old parlor trick, as they would say in the 1700s, is, you would go to this really dark room, and you could see this image is formed. Now, that's pretty cool. That this camera, just the light rays, can explain how that image is formed there. Now, notice the image would be upside down. So that the top of the shoulder of the elephant would be down here. The leg of the elephant would be up here. So you'd have an upside down image, an inverted image from this camera obscura. Now, what's so interesting, if you notice, if you study art, and you guys have some of the art classes or art history or art appreciation, we had some really, I wouldn't say photorealistic, of course, but some really wow, how do they paint something that realistic? What they found out, what they think, you must be a master painter. What they found out is, and they've done some research and looking at stuff. These have certain when you mix it upside down, rights and lefts gets flipped and stuff a little bit because of things coming in. You can actually decipher lots of times if someone basically, what they did was, they would they basically paint that image, like paint by numbers. Except it's, all right, there's their lips or something, I'm going to paint those, and we get the color just right. And if this was really bright out here, it'd be bright enough in here so they could actually paint. And you could paint masterpieces. Like, wow, how did they get that? The person would have to sit perfectly still, of course, or the background or whatever. Maybe you paint the background first, and then you have a person sit there and you overlay that over them. You paint over that part. But it actually is a way to do paintings. And they're pretty sure that some of the paintings from 14, 15, 1600s that seem so real were done using camera obscuras. Now, is that a cheat code? Maybe. But it's pretty cool. It's pretty cool. Ray model of light, we're going to work on that in chapter 34. Lots of stuff in chapter 34. This is pretty straightforward. Read the chapter on this. There's a lot of things you can read about it. Camera obscuras, they're pretty cool. You look, especially at the history of those things. All right, that's section 34.1. We're going to do reflection next, 34.2.